There, okay. No way. No way we drop it. There, okay. No way. No way we drop it. There, okay. Alright, very well. Okay, now I get in the playback of the loop and everything. Oh no, I knocked that. No way. No way we drop it. There, okay. Alright, everything seems to be working. Sound quality's good. Loudness. How loud is that really? Let me talk a little bit so I can catch the delay. Let's see. Check, 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 check. Alright, that seems to be good. Everything seems to be in line. I'm going to be working on differential equations. Granted, I won't be showing the book, but you can see that everything that I'm writing down. We're in chapter 6, section 3 of differential equations. We are using the book. Make sure. So is it OBS reconnected successfully? It's OBS. Is it OBS that's doing it? Is it OBS that has the problem? Because now what just happened? I'm still live. I'm still live. Yeah, we are still connected. So. I'm still live. Man. It seems to be a problem. Connected. Let me turn that down. I thought at one point it was my internet, but it doesn't seem to be. I think it's maybe it's OBS. Like, let's see. It's probably gonna fucking happen again. How incredibly annoying. But let me go here. Whoops, that's not what I wanted. Go here. What is my, oh yeah, my YouTube channel. Oh yeah, I'm actually live right now, also on YouTube, correct? I should be. Yes, very well, good. Good, okay. Let's go ahead and go, I'm gonna go play a video because I have to go do something real quick. Let's see, that's audio, desktop audio here. Okay, cool. So let's go like this. Start playing this. Now we have desktop audio. Fantastic.
Alright, ladies and gentlemen, welcome to the stream.
Alright, old video. I'm gonna go full screen.
Now this circuit is going to contain an inductor and a capacitor. And then we're gonna have a couple switches. We have a switch here. A switch here. Okay, we got a capacitor here. Bada bing, bada boom. And then we have another resistor right here in parallel with that capacitor here. Over here we have our inductor. Just like that, okay. Alright, so this is the circuit we're gonna be analyzing. Let me go ahead and give some parameters, some variables here. We're going to define our resistors. Let's see, we got positive, negative. We're going to define this as just V. We have what? R1, R2, C, L. Okay, so R1, R2, we have C, and we have L. Inductors are really defined by the current flowing through them. Capacitors are really defined by the voltage across them, Vc of T. Because of the way that they store energy, a capacitor stores energy in an electric field, and this has a relationship to voltage. And then an inductor stores energy in a magnetic field, and this has a relationship to the current flowing through it. So at T equals 0, right, this is going to close at T equals 0. Alright, and then at T equals T is going to open. So when T equals T, and again when T equals T, this is going to close. T equals T. Okay, again, some arbitrary value of time. I don't think it even specifies. Okay, so let's hop into the problem. Let me explain a little bit what's going on. Until time T equals 0, both switches are open, and the circuit is initially at rest. We don't have no voltage. We don't have no current stored up, or no current flowing, no voltage stored up, except in the resistors, which we have a voltage divider, right? Two resistors in series, we're going to have a voltage divider, and this is defined by the voltage divider relationship, which you could define in other ways, but it's so common that it's worth remembering the voltage divider relationship. So both switches are open, and the circuit is initially at rest for T equals 0. Okay, at t equals 0, switch S1 is closed, but S2 stays open after a very long time, capital T, S1 is open and S2 is simultaneously closed. What is VC of t during I guess we'll write it, during 0 t t. Okay, so that's what we're about to define right now. RC circuit. So what we're going to do is we're going to convert into our Thevenin equivalent right now, because really we just want an RC circuit where we have one resistor in series with our capacitor. So to convert that into the Thevenin equivalent, we're going to look at directly across the capacitor. Yeah, I'm going to need the voltage. Okay, so we're going to say that V Thevenin equals, and as I said, you know, here comes the voltage divider relationship just right off the bat like that, boom bang, is that we just want the voltage across this resistor because it's in parallel with this capacitor, therefore the voltages are equal. Okay, Kirchhoff's voltage law. The voltages around this loop sum to 0. Voltage law, KVL. KVL. Put that in letters so we, you know, so we see it, perceive it, and think about it a little more. So now, in order to define the voltage across this resistor here, we're going to use the voltage divider relation. Okay, so this is just simply going to be the input voltage V. Since we're going across R2, this is going to be in the numerator, R2, divided by R2, the sum of R2 and R1. Okay, so that's our Thevenin equivalent voltage. Now we got to define the Thevenin resistance. Thevenin resistance, R sub TH equals, okay, so again, it's the resistance perceived by the capacitor itself. This voltage here, because it's a voltage source, it's going to become a short. If it were a current source, it'd become open. Let's draw another model. We're going to short that. We're going to have this resistor here. That's going to go to the capacitor. We're going to have this resistor here. Just like that, we want to know the resistance R Thev perceived right here. Okay. So that's pretty much what we have, and then we'll put ground for reference. So if this is what we have, then this just means that these two resistors are in parallel, okay? It's really going to be is 1 over R1. This is the way that you add resistors in parallel. 1 over R1, 1 over R2, and then this is all under 1, which we can write like that. So this is going to equal R2, it's going to be like, and then we'll just reverse it. So it's going to be like this, ultimately. R1 plus R2. Okay, so that's what R Thevenin actually equals. Okay, like that. So we have V Thev, we have R Thev. Okay, so now let's draw our new circuit. It's just our simple RC circuit. This is what we wanted. Which the Thevenin equivalent circuit looks exactly like.
Hold on. Bro. Hold on. Bro. Yeah, my OBS just won't stay connected. Holy shit. That's gonna drive, like, I holy shit. I have 2,775 kilobytes per second right now, right? This is my bit rate. So tell me how it just drops to 0. Does anybody know? Anybody know? It looks like I have 4 of you in here. I got this bullshit comment about, what does that even mean? Come to us? What does that even mean? Come to us. Come to us. And on some whatever that fucking link is. Oh, brother. Alright, but, you know, if I can't do the drop in bitrate shit, man. I don't even understand. I don't think it's is it my internet? I'm not really sure, but here, I'm gonna close this. Alright, cool. Alright, I don't know, let's get on to it, move on, get it into the actual content, perhaps. We could have some, wait, can I pull up the comments? Let me actually get back to this. Fuck out of here. Pull this up. Why is it loading like that? Okay, cool. Okay, cool, now we're rolling. Come to us. Oh, yeah, okay. Sure. What are you gonna do? Give me a virus? What do you want me to come? What are you asking right now? Alright, very well. Alright, yeah, so we're working on differential equations. How difficult is that to see? Is that difficult to see? It's a little bright. Let's go go ahead and turn down the exposure. So I'll configure that. Get that out of the fucking way. That kind of looks like garbage. Move that. You can see all of that. That doesn't look very good either, but oh well. Okay, camera control. Let's go exposure. Take this off. There. That's probably better. Apply. Let's do a little zoom. Apply. Gosh, can you guys read that at all though? What? And then I could like move that as I need to. Move him a little bit. Move that as I need to. Zoom in. Yeah. Yeah, let's do that. Let's zoom in more so we could actually read it. Okay. All right, very well. Now check this out. Okay. Oh, you guys couldn't see it. Now you can. All right. This is what we're working on, differential equations. We're reading the book, and the book that we are reading is Fundamentals of Differential Equations by R. Nagel, Edward Saff, Arthur Snyder. Okay, very well. So this is the point at which we are. We're defining solutions, particular solutions, by taking the differential operator of the differential equation and doing a little manipulation in regards to this. I'm just learning this. It's chapter 6, section 3. So we're going to go ahead and move forward, working with that. I'm kind of blocking a lot of that, ain't I? I wonder what I could do there to change that. I'm going to have to change a lot, though, to do that. Oh, fuck. Nah. I mean, not gonna do it. So, but then that's just gonna keep moving that. We'd have to like do that, or keep that up there. Yeah, perhaps that's what we can do. Small window, but it's possible. What's the quality like? Is it just me? Let me see. Can I change my quality? Let's do 720 pixels. Fuck, that's still kind of garbage, is it not? You can read it a little bit, but it's still pretty bad. Oh man, that really sucks. Fuck. Yeah, forgive me guys, I'm still just trying to figure this shit out, so. Brightness. IQ max. I had 4 people join in, now nobody else. I wonder what it takes to keep the attention of the people. Is it because I'm doing math? Probably. That looks like fucking garbage, so. Actually became easier to read. More exposure. Less brightness. Huh. Yeah, that looks pretty nice. Let's give that a try. Looks pretty good. So you guys mess with differential equations, you like mathematics, I'm studying electrical engineering, so this is what we're working on. Does that look like shit, or does that look okay? We're gonna do a bit of IQ maxing today. I guess maybe I shouldn't do that. Circuit analysis. Fuck. IQ max. Absolutely. A little dark. Okay, and OBS just keeps fucking dropping. Alright. Okay. OBS just keeps dropping. Alright, I don't think it's my internet. What the fuck is wrong with OBS? I don't think it's my internet. It's just gonna keep fucking happening too. Okay. I want to see the brightness change on there. Maybe that'll be better. Yeah. Okay. All right, and so the general solution to 9, equation 9, given by, so we're gonna general solution given by y equals c1 e to the negative x plus c2 plus c2 e to the x plus c3x ex plus c3x e to the x squared e to the x c4x squared e to the x plus c5 sine x c5 sine x plus c6 cosine x. All right, we're going to get into some more examples and then we'll actually understand what the fuck's going on, okay? So this is precisely the solution form generated by the methods of chapter 4. The first two terms are the general solutions to the associated homogeneous equation. Right. And the undetermined coefficients. And the remaining 4 terms express the particular solution to the non-homogeneous equation with undetermined coefficients. Substitution of 10 into 7 will lead to the quoted values for C3 through C6. And indeterminate values for C1 and C2, the latter are available to the initial conditions. Note how the annihilator method automatically accounts for the fact that the non-homogeneity x times e to the power of x requires the form in the particular solution by counting the total number of factors of d minus 1 in the annihilator and the original differential operator. Yeah, that's what's happening here. Okay. So, okay, I guess that makes sense. Bro, holy shit, there's no way. Still too dark, right? Let me see what it looks like on the phone. I gotta see what it looks like on mobile. Man. Still looking like shit. I just can't get the quality of the second camera right as far as, being able to see all of the letters and numbers well. Alright, well. Alright, let's fucking figure this out. Okay. Alright, let's go ahead and figure this shit out. Cool. I really have to show all of that. Huh. Alright, this should work. Okay, let's fucking figure this out. It's been like every like 4 minutes it happens. Cool, it just keeps fucking dropping. Holy shit. Actually, here, we'll do this and then go here. This is incredible, guys. Absolutely fucking incredible. Yeah, because we have to keep restarting. That's why. Holy fuck. I'm trying to figure this out. I keep dropping from 2,700 kilobytes per second down to 0. It keeps happening periodically. So I'm trying to figure out why. My OBS is being a little bitch. I guess it can't handle the fucking... I don't even know. I don't know. Is it my internet? Is it truly my internet? Here, let's do this. Okay, cool. That's not what I wanted. Holy fuck, I'm retarded. Where? Oh, okay, that's why. Fuck, I'm retarded. Okay, here. Let's do it. So, okay, so now what? Just gonna go ask AI. Fuck it. Let's do it. Gonna ask Grok. Yeah, that's fine. My OBS. Okay, I am trying to stream and my OBS keeps dropping from 2,700 kilobytes per second to 0 kilobytes per second, therefore ending the stream for a moment before restarting. Let's say dropping periodically. Keeps dropping periodically from, because it's like every 4 minutes, or maybe 5, you know, it's like every 5 minutes, it's periodically. I did an internet test and attached my results. Are the results acceptable, or do the results prove my internet is incapable of supporting streaming on OBS. Okay, let's attach the results. Wait, there, boom. Okay. Alright, let's see what fucking Grok has to say. Come on, give me something to work with, Grok. Give me something to work with. Also, some exciting stuff. I got a Raspberry Pi. So show a little bit of that. I guess here, let me switch over to this. We'll see what Grok has to say in just a second. But check all this shit out. Got well, that's just the case. But got the Raspberry Pi set up, so we're gonna do a little prototyping. Word, Raspberry Pi 5, fire, good shit, good shit. This didn't come with this. This is just something else. I got some transistors, BC547B. I don't really know much about the specs on these. And again, you know, just this shit. This is another a cooler that comes with a heat sink, because the Raspberry Pi, well, the case itself only comes with a fan, not a heat sink, and so this is essentially something that you should you would rather use that. So yeah, that's gonna be sick. I'm gonna do some prototyping with that. It's gonna be a lot of fun. Gonna be good. Maybe something that we can turn to a product. Put it on the market, because truly this is what my intention is to develop a technology company which manufactures and produces technology. But first thing first is I need a product. Correct. So let's see what Grok has to say. No, your internet speed test results do not prove that your connection is incapable of supporting streaming and OBS okay. In fact, the numbers suggest your upload speed should be sufficient for that bitrate, with some room to spare. Your test shows, blah, blah, blah. You're trying to stream, okay. A common rule of thumb, megabytes per second. 2.7, right, wait. 2.7 megabytes per second. Yeah, right, because 2,700 kilobytes per second. Yeah, okay. Factor conversion. Okay. A common rule of thumb for stable streaming is to aim for an upload speed that's roughly 1.5 times your target bitrate to leave headroom for overhead. Blah, 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 blah. For content, on typical recommendations, typically for Twitch, most common platform for blah, 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 OBS users. Okay. Is lower end. I want 1080p. Should handle it fine. In theory, the periodic draw is strong. A network instability, not insufficient speed. This happens even on connections with plenty of bandwidth. If there are brief outages, packet losses, jitter, or routing issues, Wi-Fi instability. Well, I do use Stream Elements. I don't think it would be this. I mean, I have other tabs open, but it's not really gonna consume so much of my, I guess, network usage. I don't think so. It's not like I'm running anything. I mean, if I am running the stream, perhaps, but like I don't think that's what would cause it. As far as ISP routing, I don't know. I do have a VPN running, so maybe I should turn that off. Why did it disappear? I do have a VPN running though, so maybe I should turn that off. Let me go ahead and do that. Let me just go ahead and turn that off, I guess. I mean, I'm not really trying to hide right now, so whatever. Okay, I'm not logged in. It's probably not even active. I'm not logged in. It's probably not active, right? Fuck. I don't know, I guess let me stop streaming myself, right? Or like trying to watch the stream, because I'm trying to do both. I want to make sure the quality is good. Other things I should look at are my OBS settings, because it makes sure that it's right. It's set to operate. Look, I'm dropping bitrate. It's about to end. It's about to end, right? Yeah, it's about to end. Fuck. Settings. I don't think I can change settings right now. No, I can't, because I'm streaming. Oh man, so upsetting. So upsetting. Well guys, I do have some videos on YouTube. You could take a look at those. I'm streaming on YouTube currently right now too. Let's see what's happening here. Nope. Oh man. Okay, maybe we won't. Let's hope that we don't drop bitrate anymore. I'm just gonna close out all of that. Yep, we don't need that. We'll keep that open for now. All right, let's just get rid of all of that. Get rid of that. Okay. Whoops. Okay, yeah. Let's just get back to this. Let's hope that the bitrate doesn't drop again. We're going to get back into differential equations. I don't know, maybe you're going to find it incredibly fucking boring, because I wouldn't blame you if you did so. But that's what I'm working on. Hey, right, so I'm going to just stream what I'm working on. Hope that you enjoy it. I will be working on projects and stuff like that in the near future. I don't know what, and I can't really guarantee anything, because I have actual jobs outside of this. I wish I could do this for full-time more often, but in all honesty, I'm really not that good at it. You know, still a rookie in the game. I really don't even know. You know, I'm not really sure how to grasp the attention of people. What does it take, you know? Am I meant to Jester Max or something along those lines? I really don't want to do that. I'd rather IQ Max, right, as the title of the stream indicates. This is what we're all about. So let's transition on over here. I hope the quality is decent and that you can read this. And let's continue forward. We're going to do another example. I'm still like just learning this section, so I don't actually know what I'm doing, but I'm learning as we go, okay? So I kind of, you know, I do examples on one side of the page, and then here are my notes in regards to the chapter on this side of the page. So we'll flip it over and continue the examples for this section, chapter 6, section 3, right here. All right, this is example number 3. Example 3. Perfect, that's a good... We could give some more lighting too. Just like that. That's nice. That was very nice. Okay. Watching that down here. Alright, cool. So, example 3. Find a general solution using the annihilator method 2. Alright, cool. So, we're using this annihilator method. Let me try to describe it simply. The annihilator method is a method of solving a a particular solution to a differential equation, a non-homogeneous linear differential equation, through the use of differential operators, right? So, okay, so let's go through this problem and we'll kind of see if we can describe that better. Because, to be honest with you, I don't really know I don't really know what's happening right now. To be real with you, but... yeah. So here's our differential equation. We have a third order. This indicates, you know, second derivative plus 4y, which is just a single y. That's not a derivative. That's just the base equation. X, E, well, I guess base dependent variable. Dependent, and x is our independent variable. The associated homogeneous equation takes the operator form. Okay, so now to truly indicate this, it takes operator form. First I want to know what my roots are. So let's first define the roots, and we're going to do this by essentially plugging in r for y. I'll show it by example. How would I describe that? So r cubed minus 3r squared plus 4 equals 0. So this is what we have. Okay, so we're just going to take a couple of guesses. We're going to say 1 minus 3 times 1. Okay, so we're going to make this negative 1. Negative 1 minus 3 is negative 4 plus 4 equals 0. So negative 1, r equals 1. You know, or if we said r minus 1 equals 0, I guess I shouldn't have put in parentheses. The root r minus 1, r equals 1 would make this equation true. R equals 1. No, that's not true. R equals negative 1. So forgive me. Okay. And the reason that is because if we plug in negative 1 in for r, then this equation does equal 0. Negative 1 to the third power, we still have a negative because it's an odd exponent, and so it's still going to be negative 1 minus 3 times negative 1 squared would be 1. It would come out as positive, but we have this negative here, so negative 1 minus 3 is negative 4, and then we're going to add to 4, that's going to be 0. So negative 1 will make the equation true, so r plus 1 equals 0, r equals negative 1. Okay, so r equals negative 1 is the root. Now we're going to use synthetic division to divide this equation by this root of negative 1 to get another equation which we can solve for our other roots, okay? Because we have more than just this one root. So what that's going to look like is we're going to pull out the coefficients. First is going to be r cubed coefficient is 1, negative 3, we have to put in a 0 for the missing r, just by itself, the single r to the power of 1. And then we're going to put the 4. Just like this. This is synthetic division. Go like that, make it a little easier to understand what's happening. We'll draw out this. And now we're going to -1. Shit. Now he gets pulled down, and I think -1 would go here. So -1 times -1 times 1. 1 times 1 is going to be -1 minus 3. That's -4. -1 times -4 equals, wait. Shit. That doesn't make any sense. Fuck, what am I missing? Yeah, r equals -1. Because it would make that equation true. Yeah, that's going to come down. -3. -1 times 1. -4. I'm like, I'm almost there, but this -1 times. What the fuck? That don't make any sense. No. No. What am I missing? Oh my gosh. I actually don't know what the fuck I'm missing right now. Oh no, I think I've gone retard. This isn't good. This isn't good at all. Yeah, because I gotta fully understand what's going on. I think I have to solve for my roots first in order to know exactly what I'm going to plug in for this equation. No. Come on. What am I missing? I mean, everything I've done so far pans out. So, it's a -3. That's exactly what we have here, right? Yeah, -3 plus 4. Yeah. That's a 1. So -1 is our answer. -1 minus 3 plus 4. That works. It truly works. No. And it is, it's the root. Yeah, we're going to pull down the first one. It's the root times 1. 1, because it's always addition. -3 plus -1, -4. -1 times -4. It's 4. 0 plus 4. 4 plus 4 is fucking 4 times. Ah, shit, never mind, guys. 4 times -1 is -4 is 0. There, okay. I was having a brain fart. Holy shit. Kind of retarded. Okay. Yeah, see, nobody seems to like this. Everybody's popping in and popping out. Okay. So, now we're just going to keep the stream going. I could record this, but I feel like this isn't. It's not like this is a good video or anything. Just kind of doing it, having fun. Okay, so this is where we're at, working on the differential equations. We're IQ maxing, you heard. So, okay, what's next? So now this is our new equation, just as we set that up before. So now r squared minus 4r plus 4 equals 0. Okay, so now here, let's say, I don't know, we're just gonna throw in 2 for the shits and gigs. 4 minus 8, okay, 4 plus 4, yeah. Yep, that'd be it. So r equals 2. Now wait, actually, before I do that, wait. Never mind. R minus 2 times r minus 2. Yeah, so r minus 2 squared. So we do have a double root. Okay, so we have r1 equals -1, r2 equals -2, wait, no, +2, r2 equals 2, r2 equals r3 equals 2. Okay, so that is true. Okay, so we found 3 roots, and we have a double root. One of them is a double root. Okay. Okay, one is a double root. Now, what is it that we want to do from here? So now I want to indicate, yes, indicate that. Okay. First, let's go back and look. What kind of, what the fuck, what do we call these again? So we want to look at this here. So, annihilator, linear differential operator A is said to annihilate a function f of a of f of x, a f of x equals 0 for all x, that is, A annihilates f if f is a solution to the homogeneous linear differential equation. Homogeneous equation takes the operator form, yeah, d cubed minus 3d squared plus 4. Right, d plus 1 d minus 2 squared. Because squared y. Now that's the tricky part. That's the interesting part. Sure, I could set it up like that. So we'd set it up like that, and then now d minus r, which is 2, d minus 2, m, d minus 2, d plus 1, d plus 1, d minus r, d minus r. For cosine sine, we don't have that. We only have this, d minus r, because we have a -1, d plus 1 to the power of 1 because, and now that's the double. Okay, so d minus r to the power of n. Okay, so we're going to use the operator d for, you know, for this non-homogeneous equation, non-homogeneous for the fact that we have something on the right side of the equation, right? It's not just 0. Homogeneous would be the case if we were to equal 0, but we have a value on the right side of our equation. So we're going to consider the operator d minus r to the power of m. I think it's like of f, or I don't know how to like say that in English. It's not really of, I don't think, but it's operator. I don't know. I'd have to figure that one out. Actually, I should, because when you're able to express these mathematical operations in English, it becomes a lot more intuitive and you actually grasp it and understanding. This is a bit I don't know, arbitrary, not really, ambiguous perhaps is the correct term, but yeah. Okay, so this is going to be our method for the solution because of this particular value we have. And so we solve for our 2 roots, and now that's going to become d plus 1 to the power of 1 because it's only a single root, and then we have this double root, which is d minus 2 to the power of 2. And that's what we're getting here, right? Yes. Y equals 0. Okay, very well. The non-homogeneity, x times e to the power of 2x is annihilated by d minus 2 squared. Therefore, every solution of 11 also satisfies. Oh yeah, we can rewrite this too in the operator form. Oops. Let's do that so we get used to it. Like that. And we can plug these in. D plus 1. D minus 2 squared. Do that again. Y equals 0. And now why that one? Why do we not consider d plus 1, but we only consider d minus 2 squared? Therefore, every solution of 11 also satisfies. Every solution of 11 also satisfies. Why, though? Why is that the case? Equals 0. A general solution to 13 is. Damn, what the fuck? What is actually happening here? Maybe we'll have to ask AI and see what they want to recommend. Let's see. I wonder what's happening over on the YouTube. Let's go over there and see. Probably nothing. Seems like we haven't dropped bitrate though, which is really good. And the quality looks pretty nice. Why is that? Like gets worse near the edges. But it was almost good. IQ Max. Mucka Live. IQ Max. Sick. Brother. Sick. Okay. Alright, so where were we? Yada yada yada. That. And now y d minus 2, the non-homogeneity xe to the power 2x is annihilated by d minus 2 squared. Therefore, every solution of 11 also satisfied is eliminated by this. But why? Why this one and not d plus 1? Is it because it's in the... Oh, well, because I guess that's the form. It's in the actual form. Not really. Okay. Alright, I guess that's fair. Okay. So, is annihilated by, therefore every solution of 11 also satisfies. Okay, so let's go ahead and write that. So, d minus 2 squared times d cubed minus 3d squared plus 4 y operator y, some shit like that, equals d plus 1. Okay, we're multiplying to both sides, of course. D plus 1, d minus 2 squared. Oh, wait, to the 4th. Because we got to multiply both sides. To the 4th, y equals 0. Okay. Alright, a general solution to 13 is, and now we just go straight to our general solution. How? How and why? How and why did that happen? How and why? Right, we have x e to the 2x, right? C4, that's our, so our non-homogeneous solution is this. So our general solution is this, and our non-homogeneous solution is C1 e to the negative x. You know, using our roots, our defined roots that we found earlier, these are going to give us, you know, if we look to the general solution, or if we jump to the solution to the the solution to the homogeneous equation, considering, you know, we assume a solution of the form of the exponent to the power of our root. Okay, so the exponent function to the power of our root. Okay, we assume this solution. So the solution to the homogeneous equation, which is a part of our general solution, the general solution consisting of the sum of the homogeneous solution and the particular solution, the homogeneous solution, when setting our equation equal to 0 and solving for our roots, such as we did earlier, then we're going to go ahead and plug our roots in, assuming the solution a constant multiplied by the exponential function to the power of our root. In this case, our roots are -1, and we have a double root of 2. The double root leads to us leads to this. So plus C2 e to the power of 2x plus C3x e to the power of 2x. Okay, this x here is the resultant form given a double root. Okay, that's the resultant form. So now our particular solution is the reason we are doing this operation here, are using these operators. Okay, so this is a new method of solving for the particular solution. Now, this is the particular solution. I'm going to put a little space here so we understand what's happening, because I actually have yet to figure out what's fully going on. We're grasping it as we go. 2x plus c5 plus c5x to the x squared, x to the third, e to the power of 2x. So now, okay, we can solve for C4 and C5, but we need initial conditions to solve for our homogeneous solution, for the coefficients to our homogeneous solution, that being C1, C2, and C3. We need initial conditions to solve for those. But, you know, we are capable of solving for these coefficients of C4 and C5. Or so we should be. Yes, we are. We are capable. But what I'm trying to understand is really like where the solution comes from. I can kind of see it. I can kind of see that, you know, we ended, considering our double root, we ended with an x here. And so we have to go move on to x squared. And then, of course, we have an x squared, so we have to move on to x cubed. And we maintain this e to the power of 2x, which makes sense to me. But what relationship does this solution have to our operators and everything we did here? That's what I'm not fully grasping yet. So I really want to know what's happening there. And in order to understand that, I guess let's go back to our notes. Let's read our notes again and try to understand and comprehend what the fuck is happening here, because it just doesn't make sense, right? It just doesn't really add up. All right, unless you're following, go ahead and comment and tell me what's happening. So, right, non-homogeneous linear second order constant coefficient equation. Our operator equals, our operator equals, right. Satisfies. Satisfies. Yep, each is annihilated by a differential operator with constant coefficients. Each non-homogeneity is annihilated by a differential operator with constant coefficients. By a differential operator with constant coefficients. By a differential operator with constant coefficients. Annihilator. A linear differential operator A is said to annihilate a function f if a f x equals 0. If a f x equals 0 for all x, that is a annihilates f if f is a solution to the homogeneous linear differential equation 2. Then the infinity. That really doesn't tell me anything. Alright, let's go ahead and keep moving forward because perhaps we may fully understand as we move on. Okay. Comparison with 12 shows that the first three terms of 14 gives a general solution to the associated homogeneous equation. And the last two terms constitute a particular solution form with undetermined coefficients. Direct substitution reveals C4 equals negative 1 over 18. C5 equals 1 over 18, and so general solution to 11 is plus the annihilator method then rigorously justifies the method of undetermined coefficients of section 4.4. It also tells us how to upgrade that procedure for higher order equations with constant coefficients. Note that we don't have to implement the annihilator method directly. We simply need to introduce the following modifications to the method of undetermined coefficients for second order equations that was described in the procedural box on the page 178. Not going back. That was the end of 6.3. Holy shit, 6.3 is like 2 pages. That's incredible. Okay, so here's a little outline of the method of undetermined coefficients. I think I have enough room here. Literally could get it all on one page. That's incredible. Oh, whoops. Alright. So probably going to finish this up, maybe attempt the homework, and then probably going to go gym. Probably gonna go gym. Do that. Let me see what's popping off here. Let me see what's popping off here real quick. Nothing. Did it keep the whole thing? How long has this been going for? Yeah, it did pretty much. Cool. What's the, yeah, 720p, is it? Cool. Super cool. Super cool. Man, I can't believe that. The synthetic division almost got me, man. I just couldn't figure out what the fuck I was missing, but we got it. We got it figured out. Okay, yeah, so... Alright, so we're just gonna go ahead and write this down. The method of undetermined coefficients. Let me get rid of that again. Method of undetermined coefficients. I hope I have enough room here. Let's see, can you see that here? Method of undetermined coefficients. Perfect. Undetermined method of undetermined coefficients. Okay, to find a particular solution to the constant coefficient differential equation. Okay, so yeah, we're just gonna write find particular solution to no, that's all I want. Ly, this is our operator, equals cx to the power of m times e to the power of rx equals cx, I already forgot, to the power m times e to the power rx, where m is non-negative integer, use the form, blah blah blah. Then y, our particular solution of x, motherfucker, of x equals x to the x to the s? Oh. X to the power of s, a mx to the m, a sub mx to the power of m, plus yada yada, plus dot dot dot, plus a1x, you like it? You like it? A naught, you like it? E to the power of rx, e to the power of rx. Alright, now I think that's looking good. With s equals 0 if r is not a root of the associated auxiliary equation. With s equals 0 if r is not a root of the associated auxiliary equation. Auxiliary equation, characteristic equation, also the equation that we use in solving our roots. So that is the characteristic or auxiliary equation. Otherwise, so with s equals 0 if r is not a root, of associated, I'm gonna put characteristic equation. I'm gonna abbreviate that because a little too late in that. To find a particular solution. Okay, so otherwise take s equal to the multiplicity of this root. Okay. Otherwise s, whoops, come on. Otherwise s equals multiplicity of this root. Okay. Okay, so I think that just gave me insight into the relationship between the operators and our homogeneous solution, our solution to the homogeneous equation. I think that just gave me insight into the relationship. So now, anybody here in the stream, I know there's probably not anybody, but if anybody at all, I really appreciate you guys coming. We're not done yet. I just wanted to give respect and appreciate you being here and watching and tuning in. Yeah, I don't think anybody's watching right now. Shit. Am I cooked? Am I absolutely fucking cooked? Oh man. Absolutely cooked. At least we haven't dropped bitrate though. That's fire. At least we haven't dropped bitrate. I wonder, am I in a category? Have I categorized myself? I don't think I have. I probably should. That would be probably be a lot better for people who are actually interested in STEM, mathematics, or science, or some of that. Otherwise, I'm just gonna have like a bunch of normies coming upon me, people who watch like clavicular and shit, and they're not gonna really fuck with my stuff. But who knows? You know, possibly, perhaps. But you know, a lot going on in the world right now. I'm currently in an internship, which is going really well. Indulging in the sales side of selling precision manufactured technology. So I'm kind of working in the sales side of that. That's really cool. I'm also about to start tutoring. which is good too. I'm going to tutor mathematics, despite maybe I'm not fully competent in the differential equations, at least not yet. You know, this is one of my current classes, so we're working on it, but we are grasping it as we go. Thus far, I think I'm doing really well in the class. I think once the grades of my 2 previous quizzes, and then I just took one of the midterms, so we don't have the grades on that yet, but once it does come out, I believe I will have an 8 in the class, be around like 90 something percent in the course. So that's going really good. I'm also in digital systems. I'll show you a little bit of those notes. The last thing that we learned was ROM. How do we describe it? I think I forgot, but ROM. And previous to that, we learned about multiplexers. We learned about encoders/decoders. So it's actually really sick. Here's some cool drawings. This is the type of stuff that we're working on in digital systems. So I don't know. I would really love to just stream while I'm studying. Of course, it'd be a lot better to do some more thought out content. Of course, you know, like actually work on some projects or something that's a little more interesting than just me studying, of course. So I'd love to do that. I've done videos you can see on my YouTube channel of essentially lectures. I've done like one project video, but it's kind of shit. I have a robot that I made, and I wish I would have recorded that because I completely designed it in Blender, which is a joke of a CAD. I know people joke about it, right? But I actually use it for a CAD, so I mean, I find it worked well for me. It got the job done. And I did the circuitry of the robot and everything, and I did the programming, although, you know, of course, I'm not the best of programmer, so I used AI to assist me. You know, right, use the tools which are at your disposal. So this is something I have to go back and refresh, the buffer, just its operation, essentially. Now we're getting here to the 4 to 10 decoder, okay, 8 to 3, priority encoder, this kind of stuff, and then read-only memories, ROM. So that's where I left off, and I have a lot to learn here still. I've taken the notes, but like I haven't really learned it, you know what I mean? It's 2 different things. So read it once and then go back and study it. It's going to work well for you. I wonder what you guys have going on. You know, granted, I don't think anybody in here, but if you are, yo, I really appreciate you. Comment. You know, don't be a fucking stranger. Comment or something, say what's up. Let's see, I'm gonna go check in on Kick again. Go to my channel on Kick. What? How do I lose a view? 4 views 1 hour ago? Maybe because of the times that it cut out. It literally said 6 views, but whatever. I wonder, does Kick maintain your video, your stream after it's done? You know? Does it have like a history and maintain it? Because YouTube does. You can go back and watch those streams. I don't know if Kick does though. So we'll figure that out. But very well. So let's conclude this. I wasn't finished writing down everything. Let's conclude this. Yes. Get rid of that so that we don't drop bitrate again. Bitrate's been holding up though. That is a God blessing. So that's beautiful. Okay. Multiplicity of this root. Yes. To find a particular solution to the constant coefficient differential equation, where it's just a little different, use the form. Okay. Particular solution to Ly equals cx to the power of me, okay, x to the power me to the power alpha x cosine beta x, or that, or beta does not equal 0. Started from the very beginning. Okay, and we drop bitrate. Cool, you fucking cool. 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 Drop bitrate again. Cool. Love that. Really love that. Oh no, we drop bitrate again. Oh. This thing really got such a small... I don't know, try that. Let's try that. It seems to have like a point of focus, you know, right in the center, a central point of focus, of course. But like, why does it have to blur everything on the edges? It seems to continue to happen, so it's quite annoying. Okay. So this is our solution. Here, let's go back here. Get rid of that. Okay, we're back here. Particular solution equals x to the power of s. We got the same thing, except this time now this is going to be our coefficient too. Okay, yeah, sure. X to the power of m plus dot 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 plus a1 x plus a naught e to the power of what? Alpha x cosine beta x plus, yeah, okay, and yeah, we'll write it plus x to the s times b sub m x to the power of m plus dot 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 plus, whoops, I almost put a, shit, I put a, b1x plus b naught e to the power of alpha x sine beta x. And now this solution comes from a conversion. You know, we say e, so essentially it's like the exponential function to the power of an imaginary number. And you'll see if you go through differential equations, you'll see what I'm talking about, or if you know what I'm talking about. But you know, we have an exponential function to the power of an imaginary number, to the power of an imaginary number. We could say an exponential function to the power of an imaginary number. We're going to use Euler's formula, and this will convert it into one of cosine, into a sum of cosine and sine. And so essentially that's where this form comes from, right? Because we always assume the form, like the first form that you learn is assumed to be one of an exponential function to the power of the root. And so sometimes our roots will consist of imaginary numbers, and then from there we use the Euler's formula to convert into cosine and sine functions, trigonometric functions. It's actually beautiful. It's a beautiful equation. It's a beautiful conversion. So it's really sick. You know, maybe we'll go ahead actually and continue. Now let's go put all of this into practice. This is literally it for this section. So let me see how this quality is. It's a little bright up top, but I'm not gonna worry about that. I want to go in here. Let me go to kick on my PC and see what it looks like on here. I want to see how well it looks. Please, 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 please. Maintain bit rate. Maintain bit rate. Man, it's a little fuzzy, right? It's a little fuzzy. I want 1080p quality. Oh, it's kind of unacceptable. I got like $60 cameras though. Ain't gonna lie, so that might be my problem. Oh fuck. The stream completely ended. Oh my gosh. Yeah, because now it says I've only been going for 5 minutes. Oh. Oh no. What does YouTube say? Oh, bro. It does save your old streams though, because it is still on there, 1 hour and 12 minutes. Why did this one end completely? My bitrate has dropped multiple times. Why did this one end completely and the previous one didn't? It just doesn't even make sense. It just doesn't even make sense. How long has the YouTube stream been going? Has that been persistent? It has. That hasn't completely dropped at all. Interesting. Alright, yeah, let's go to my homework. And let's see if we can do this. Let's see if we can do this, because I think we have all the tools necessary. The homework's usually some seriously long computation, though. What time is it? 1:48. I want to go gym, but we should knock this out first. Okay. All right, so we've essentially we've covered all of section 3, chapter 6, section 3 in our differential equations book. So now we're going to go ahead and apply the knowledge that we have acquired, and we're going to complete the homework. We're going to complete the homework. Perhaps, you know, if we need some assistance, we'll call an AI, but I don't think that we will. I think that we're going to be capable of doing this. And it's going to be fun. You like math? It's going to be sick. You know, we're going to do some computations, calculation. We're going to crunch the numbers. And, okay, I'm a numbers guy. All right, so we're going to be on that shit. On this type of timing. What do I need to do? Oh, yeah, okay. All right, so we're going to keep this out to call on. And I'm going to grab another notebook that we're going to do the calculations in. This right here. Here we can go through a little bit. You can see some of the other shit I've done. Just a little review. That looks like calculus. Oh no, that's separable equations, right? Separable equations, I'm pretty sure. It's a little drawing I did. I mean, I've pretty much discontinued, but like I still have the file for the 3D model, so perhaps I will see it to fruition. More differential equations. These are some pretty long ones. That's a common emitter amplifier for, you know, the purpose of an oscillator, a Colpitts, or that was the Hartley oscillator, actually. Yeah, that's the Hartley oscillator, but I want to do the Colpitts, and I actually recently acquired some crystals, some you know, I assume quartz crystals, piezoelectric crystals, and we're gonna probably use those as our active component in the oscillator. Would you consider that an active component? Maybe not. Or is it? No, because I was thinking about it, and we're gonna need the transistor regardless, because that's a part of the amplifying circuit, not the like oscillating circuit. Granted, it's all one, you know what I mean, but like that's not the yeah. So I plan on doing that. Obviously, I should stream it, so I'll be here for that. More differential equations, using matrix operators. Computing the Wronskian for the purpose of determining whether whether these two variables are dependent or independent. So we can do that. We can also use the Wronskian to solve for our variables such as x and y. We can use the Wronskian to solve for them by taking the determinant of the initial matrix divided by as the divisor from the determinant of the resultant matrices from plugging in the vector, the solution vector. Fuck, I don't know how to refer to it, but whatever. Let's just stay on track and do what we're working on now. Section 6, or chapter 6, section 3. Okay. So mathematics it is. Mathematics it is. Whoops. Okay, so this is our equation. We have third order derivative, second order derivative, 3y minus x e to the power of x. That's all I wanted, equals x e to the power of x plus 13. Plus 13. Okay. Yep. Yeah, it looks nice. It looks really nice on here. How does it look on here? It looks decent on here. Decent. Not very good, though. Okay. Plus 13. Now we got this constant in here, so I think that's only going to contribute, though, to to finding our values of the constants. So we're going to go ahead and set up the characteristic or auxiliary equation first, like this. Can you see that? Yeah. Because I want to solve for my roots and see if we have double roots and, you know, whatnot, equals 0. Okay, so we're going to assume some solutions to this equation. We're going to plug in some numbers. So I'm just going to say 1 initially. 1 cubed 1 plus 1, 2 is 3. 1 plus 2, 3. Yep, minus 3. Okay, so r equals 1. That works. Okay, so now we're going to use synthetic division and divide this. We're going to pull down the coefficients. 1, 2, negative 3. Dividing by 1. Yeah. Okay, I guess we'll just go like that then. This comes down. Now we're going to have 1 times this number here, 1. 2 plus 1 times 1 is 3. Now we're going to have 1 times 3. This, again, our root, 1, our root multiplied by whatever the preceding value was. And so 1 times 3 is 3. Negative 3 plus 3 is 0. Okay, so now this gives us our new equation of, r squared plus 3r equals 0. Okay, so r equals 0, and then we're going to have r equals negative 3. Yeah, and r equals negative 3. So we don't have any double roots. We're going to rewrite this in operator form. D cubed plus 2d squared minus 3. We'll go ahead and write it completely just to get familiar with it. Equals x e to the power of x plus 13. So just to get familiar with it. Now, e to the power of x. Okay. Okay. Now, what operators do we have here? We don't have any multiplicity. So I think like it's going to be d minus r. So d minus 1, d plus 3, and what would I do, just d, since we have a root of 0? Oh man. D minus r, so just d f. If r is not a root, if f is a solution to the homogeneous linear differential equation, method of undetermined coefficient, find a particular solution, cxyp equals 0 if r is not a root of associated characteristic equation. Otherwise, r is not a root of associated. R is not a root. Okay. So the only one that matters, I think, is r equals 1. And then it's, come on, brother. What the bit? Alright, brother. D minus 1, D plus 3, perhaps D minus 0. I'll just write it all out, whatever. So sure, we got this. Can you see that still? Yeah. Sure, so we got this. How much of this really matters though? D minus 1. I think D minus 1 would be the D minus 1. D cubed plus 2D squared minus 3. Something like this. And go to this. We would say we don't have the double root though, so it's just y x equals and then d to the 0. So we're just gonna say c1 plus c2 e to the power of x plus c3 e to the power of negative 3x. Okay, that's our solution. Considering our characteristic equation and our roots, that's our homogeneous solution, or a solution to the homogeneous equation, whatever you want to say. And then now we need a solution to the particular, particular solution to the non-homogeneous equation, to get our general solution. So d squared, see what the fuck does that really have to do? Because I think, are we looking at that? Because what, that would be that, and then now d minus 1. Yeah, we had the multiplicity. Sure. Minus 1/18 x squared plus 13. Plus c4 plus c4. We want just the particular solution. Plus 13. Just the particular solution. If we plug that in, what would that look like? The third derivative. C4x e to the power of x. And x, it is a root, so x to the power of 1. So let's say it would just be c4x e to the power of x. I guess not exactly. Y equals. So the first derivative would be c4 times e to the power of x plus x times e to the power of x. The double, or the second derivative, would equal c4 times e to the power of x plus e to the power of x plus x e to the power of x. I want the third derivative too. The third derivative equals we're gonna combine this, so it's gonna be 3e to the power of x plus x e to the power of x, right? And then this equals 2e to the power of x plus x e to the power of x. So now if I were to plug that in, I have c4 times 3e to the power of x plus x e to the power of x plus 2 times c4. That's our second derivative. 2e to the power of x plus x e to the power of x minus 3 times c4 x e to the power of x equals x e to the power of x plus 13. I don't think that I really have this correct. I don't think this is correct, but we'll see where it takes us. Yeah, because literally how would we C4? What variable would solve for 13? Unless it were just like plus C5. Plus C5. C5 equals 13. Okay. So 3c4 e to the power of x plus 3c4x e to the power of x plus 4c4 e to the power of x plus 2c4x e to the power of x minus 3c4x e to the power of x. 3c4 e to the power of x. 4c4 e to the power of x. 7c4 e to the power of x. 3c4x e to the power of x. 2c4x e to the power of x. 3c4x e to the power of x. Gone. Plus 2c4x e to the power of x equals x ex plus 13. Damn, son. Nah, I'm not on the right path. But, shit, I think it's time to go to the gym. So I think I need to do that. I need to go to the gym, I'll come back, and I get back on it. You know what I mean? Know what I'm talking about? Oh, yeah, probably, because I'm not on the right path right now. Beep boop beep do 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 do. Oh, damn. Alright, cool, yeah, I'll be back. I'm gonna go probably gym for an hour or two and then get back on it, so